Hello, I'm Joseph Huber, and today I'm going to be talking about the work we did for optimizing OpenMP GPU execution in LLVM. Now, this was a collaborative work, so I'd like to take a moment to thank all the people who helped with this project, starting with Melanie, Giorgis, Shilei, Jose, Kuter, Barbara, and Johannes. So this is a very broad overview of OpenMP support in the LLVM ecosystem. We have the Flang and Clang front ends, which each have their own OpenMP parsers, semantic analyzers, and code generation. And those both share the OpenMP IR builder, which is a front-end independent LLVM IR generator that lives inside of LLVM. And we generate the IR to be simple and expressive so that it's easier to work with for tooling and optimizations. Now, those optimizations are done with the OpenMP opt pass, which is an interprocedural optimization pass that contains optimizations for both the host and device when using OpenMP. And ever since LLVM 11, it's been in the default optimization pipeline and can be run with O1 or O2 and above. Now, we also have the OpenMP runtimes themselves. So we have libomp, which contains the OpenMP implementations for all the regions in the host. We also have libomp target and the plugins, which handles offloading execution from the host to the device. And then on the device, we have the libomp target NVBTX device runtime, which contains the actual implementation of the OpenMP constructs when used on the device. Now, this work mainly focuses on simplifying code generation inside the front end of Clang and the IR builder. And we made this more simple so that it can be better used to do analysis inside OpenMP opt. And inside OpenMP opt, we added a lot of new optimizations for the GPU specifically that aims to close a lot of performance gaps with OpenMP offloading relative to other implementations such as CUDA. Now, I'll explain very briefly how we map OpenMP to the GPU. So GPUs use streaming multiprocessors, and each SM contains a block of threads. So each SM in OpenMP is mapped to a single team. So this team can communicate with other teams using global memory, which is typically slow. Now, each one of those teams contains a bunch of threads. And of those threads, we also make special note of the main thread, which is used to coordinate work amongst other threads inside of the standard OpenMP parallelism model of forking and joining threads. And each of these threads inside of a team cannot communicate with threads in another team without global memory, but they can communicate within a team using shared memory. Finally, we have a single thread which controls all of its own parallel work, and it contains its own local memory and registers. Registers specifically are very fast, so we prefer all memory go there if it can. Now, this simple mapping raises some problems when we try to apply the standard OpenMP semantics that were originally designed to be run on CPUs to the actual execution that happens on GPUs today. And to go over that, we have some motivational problems with an example of a standard CUDA region compared with an OpenMP one. So in CUDA, we have a blocked computation that uses a buffer to do some parallel work on this shared memory. We also have a thread private flag variable L. Now we do some single thread initialization work by checking if the thread executing this is thread ID 0, which we'll call the main thread. And then we run a barrier to that, use all of the threads in parallel to load the data, use another barrier, and then if that flag variable is set, we indicate that we have some useful work to do, and then we do parallel work with those threads. Now, the same implementation in OpenMP will be done using the pragma OMP target clause to indicate that this block will be executed on the device. Then, to map execution to the blocks on the device, we use the teams distribute clause and then a work sharing loop. Inside of that, we then have this buffer variable and L flag variable L like we had before. But because we're in OpenMP, we are only executing this region with the main thread right now because we haven't seen a parallel region. So we have no need for a explicit uh, check on the thread ID or a synchronization because conceptually it's all one thread. Then to do our parallel work, we use a standard Pragma OMP parallel for region to distribute all the work in that between the threads. And then we load the data as before, and then do another parallel work loop to then do the actual parallel work. Now, this has a few problems with standard OpenMP semantics when compared to what we would expect to work efficiently on CUDA. So the first problem is the globalization of local variables. Now, CUDA and the GPU itself have the default thread sharing method of being thread private. So data cannot be shared between threads by default. And this is in direct contrast to the memory model of OpenMP, which stipulates that all variables should be able to be shared by the threads inside of a team. So what happens is when we have a variable that could potentially be shared between the threads, we need to generate a special runtime call to the OpenMP runtime that can allocate shareable memory. And shareable in this case could be global or shared. And we can't just replace this statically with some known amount of memory because in some cases it could be unknown at some time. And we did it this way to make it more simple. Now, in this case, we see that this buffer and this flag variable need to be replaced with some runtime call allocating an amount of memory. And then we also need to introduce a free call. And now, because of this, this variable can't be private, it needs to be shared. So another problem is the execution mode itself. So CUDA uses what we call the SPMD or GPU execution mode, where all of the threads in a block are active simultaneously and execute the kernel in parallel. So this is very efficient in the standard way of executing on the GPU. However, this is in direct contrast to the standard OpenMP execution model that has been used on the CPU, which is to fork and join threads. In this model, we have a single main thread that handles all of the sequential code until we reach a parallel region, at which point we fork all of the threads to do the parallel work and then join them back together at the end to do more sequential work. On the GPU, this incurs a lot of runtime overhead and is generally very slow, so it can cause problems. So we wrote some optimizations to improve this. So the first optimization we implemented was deglobalization. So because we simplified the globalization of variables to have each variable be globalized by a runtime call, we can then track that runtime call and see the usage of the pointer that it returns. In this case, we can investigate the buffer variable. Now, if we look at its usage, we see that it is legitimately shared between the threads. So it needs to be in shared or global memory. But because the actual allocation happened, the actual allocation was only executed by a single thread. And additionally, we can see the allocation has a fixed size. And because of that, we can then statically determine that at runtime, when this is executed, it will allocate a fixed amount of memory. Because of that, we can just replace it with a static amount of memory allocated in a global variable that is in shared memory. And this is effectively the same as using the underscore shared keyword in CUDA. Similarly, you could do analysis on L, but instead of replacing with shared memory, we can see here that it's not actually shared between the threads. And in that case, we can then move it back to thread private memory, which will be mapped to the registers. And this, through these optimizations, we have basically mimicked the explicit memory allocation done in CUDA with our implicit optimizations. Additionally, the SPMD execution is much faster, so we want to be able to turn any generic that is non-SPMD region into an SPMD region if we can. And we can do this if the parallel region is active for the entire target block. If the parallel region encompasses the entire target region, then we can say that all threads are permanently active and we're basically executing in CUDA mode. But in order to make that transformation legal, what we need to do is analyze all of the side effects that happened in the main thread guard them with a conditional like this, similar to what we did in CUDA, and then turn all of the implicit barriers that used to exist from the parallel regions into explicit barriers. And doing this, we can then move our generic mode kernel to an SPMD kernel without any changes from the user. And then finally, we have runtime calls that can be folded to constants if they're known. So in this case, we have the num teams and num threads clauses, which will affect how well we can perform work sharing clauses. But because we know that they're constants, we can simply replace these with some constant value, which will improve how we do work sharing. So the way we actually implemented these optimizations was in the OpenMP opt pass, as mentioned previously. And this pass contains OpenMP specific optimizations. We run it early as a module pass, and then again late as a call graph pass. And to do these optimizations, we use embedded domain knowledge of all of the OpenMP runtime calls to then kind of map the original OpenMP semantics to the IR. So we can track OpenMP runtime calls, and we know beforehand what they mean, and then we can determine that, oh, this was the call to make a generic region, or this was the call to allocate a globalized variable. So to do the actual optimizations, we use the attributor framework to do inter-procedural optimizations. Now, the attributor is basically a framework that allows you to do these inter-procedural optimizations by iterating a condition until you reach a fixed point. So we can take some analysis and repeatedly apply it, and then once we don't change after a single iteration, we've reached a fixed point, at which point we can use that information and manifest it into doing the actual optimizations. And a brief overview of the abstract attributes that we implemented to do this work are the execution domain attribute, which determines if a block is executed by a main thread, the fold runtime call, which just simply replaces runtime calls with constant values, heap to stack, which replaces globalized memory with an alloca, as shown before, and heap to shared, which replaces globalized memory with shared memory if heap to stack was unsuccessful. And then finally, kernel info allows us to track kernels and then optimize the execution mode to SPMD mode if possible. So when we're doing interprocedural optimizations, we want to eagerly internalize all of the functions, because if we don't have internal linkage for these functions, then it's possible that some other program outside of the translation unit could call that function and then internalize that, could call that function and invalidate our analysis. So to combat that, we eagerly internalize these variables. We keep the old definitions around, but they're unused now in the module. So if anyone calls it, they'll get the old unoptimized version. But what that does is allow us to have basically a complete view per module of what this code is actually doing without needing to worry about any other things interfering. You can also get this through link time optimization, but that is another issue. So we clone the functions and replace all of the uses with the internalized version. And then to do our optimizations, we simply seed the attributor instances on the known OpenMP runtime calls. So I want to explain a bit more about the heap to stack pass. So we interprocedurally scan the use of a pointer, and we can replace it with a simple alloca, which is a stack variable, which will be mapped to a register, simply if the pointer is not captured and the allocation is of fixed size. So in this example, we seed the heap to stack analysis on the pointer returned by this OMP alloc runtime call. And then we can simply see through maybe some other analysis that this use call has the no capture attribute. That means that no one is going to make a copy of this pointer, and therefore it can't possibly be shared between the threads because it's read-only inside this thread. And because of that, we can then simply just say, hey, this is an alloca, and replace that expensive runtime call with stack memory, which will then be probably mapped to a register on the device. Additionally, we can do heap to stack by doing a similar analysis, but we can also check if it's not shared through some synchronization point, and for sure it's deallocated. So in this case, we have new attributes for no sync, will return, no unwind, which state that it's not going to be shared between some parallel constructs, and it's not going to hit an exception or similar. And then we know for a fact that it's freed. In this case, we can also replace with an alloca. And then additionally for these variables, if heap to stack doesn't succeed, we can still try to get rid of this globalization by using the heap to shared optimization. So heap to shared also uses the execution domain attributor to interprocedurally identify blocks that are only executed by a single thread. Now, if it's only executed by a single thread, then we can identify these runtime calls and replace the memory allocations with global memory of a fixed size, because we know that only one thread is allocating it, so we only need that much memory. So in this example, we have a call to the NVIDIA intrinsic for getting the thread ID, and then we compare that to 0, which is just going to be our main thread ID, and then if that thread ID is 0, we will do this region, if else we will return. So because we know that this region is only executed by a single thread, we can simply just replace this OMP alloc runtime call with a shared global variable. This shared global variable will just contain all the memory we need to do this shared memory, and then we will just replace the pointer with a pointer to that global. And through this, we can get rid of most of the globalization you'll see in practice in these applications. So finally, we have SPMDization. So what we want to do is detect SPMD compatible target regions and turn them into SPMD mode if possible. So what we do is interprocedurally track the side effects that are reachable by the main thread, that is thread ID 0. And we also check heap to stack and heap to shared for what they have to say about these side effects. So if we see a side effect, an instruction that has side effects that is reachable by the main thread, we then need to move it into a reordered block that is guarded by a conditional on that thread ID for the main thread. And then we have only one thread executing that as we had before. But then we also need to add a barrier instruction after that to then make sure that we aren't, because everything is now in parallel, we don't have implicit barriers anymore. So first we reorder the things into an optimized local guarding scheme, and then we can simply move the parallel execution to the beginning of the region, so everything is executed in parallel, and all of the local side effects that were executed by the main thread are now handled correctly, executing in parallel. So for all of these optimizations, we wanted to provide the user with extra information using remarks that Clang provides. And these remarks can indicate to users which optimizations succeeded, and if they failed, it can tell the user what they can do to assist the optimization, or the reasons it failed. And what users can do if there is a failed optimization is utilize assumptions. And assumptions were added in OpenMP 5.1, and they allow the user to give extra information to the compiler that will help with its static analysis. So on the right, we have a list of OpenMP 5.1 standard assumptions, and then we also have some LLVM extensions that we use for our own optimizations, like SPMD mode. So these remarks and the assumptions that they reference allow users to do interactive optimizations to get the most performance out of their application without treating the compiler like it's a black box. So finally, I'd like to go over some evaluation of a few mini applications for high performance computing benchmarks we used and the effects that our optimizations had on them. So in these examples, the far right bar represents a CUDA baseline, except for mini QMC where there was no CUDA baseline. And on the left, we have the base implementation, which was LLVM 12 before we applied all of our changes. So in XS Bench, you can see that we get a reasonable performance increase by applying each one of our optimizations in series. But we're still somewhat off of the CUDA performance. Now in RS Bench, simply by applying heap to stack, we have completely removed all of that overhead and achieved rough parity with CUDA implementation. And you can see in this example how much of a difference removing that globalization made before our optimizations. Now, in SU3 bench, we get most of our performance by applying the SPM deization pass because it was a generic region. Now, even though we get a very large performance increase, we're still somewhat off of the Kuter performance. And then finally, for mini QMC, we lose a lot of performance in our development branch because we simplified the implementation of globalization. So we used to do some Clang specific optimization um, of globalization, and our more simplified scheme was much slower. However, when you apply optimizations, you can now see that we not only get that performance back and then some, but we get most of that performance back. But then also when we apply SPM deization, we get roughly 2.3 times performance with just these optimizations to transform these OpenMP regions to a more efficient form for the GPU. So in conclusion, we presented a group of optimizations that are mainly used to optimize GPU execution using OpenMP. And this is mainly by taking things that are problematic from the perspective of OpenMP as a CPU parallelism method, and then using advanced analysis and interprocedural optimizations to translate idiomatic OpenMP codes to something that is efficient and idiomatic on the GPU. So if you want interested in anything further, we have official LLVM documentation and some more talks and papers on the work that we've done for OpenMP. So thank you.